Hello everyone. The intent of this video is to provide you with some solutions to selected review questions to maybe give you some hints and help you think about how to prepare your cheat sheet for the final exam. Please remember the final exam treated as a proctored exam, and you have the review here for the exam where you can omit questions 1A and 1C. All the other questions are certainly good questions to study from, but I have solutions to selected review questions. I called it. There's a template in the guided lecture note section, and I'll be showing you the solutions to those. And they come from this review packet. And the answers, of course, are on the second page of this review packet, as you can see. So there's the answers. But in any event, please restrict yourself to only the Laplace Transform table that's I emailed you about, and it's posted in Blackboard. I don't think it's posted in Blackboard because Blackboard has it's kind of funny sometimes when you take photos the way they download. So I had emailed you this table with all the Laplace transforms, and also in the bottom right corner there's the common series that we encounter. So as you've been watching the lectures, obviously we were using this exclusively. But this is your cheat sheet for the final exam, and feel free to write anything you want on the back of it. The only rule, it has to be handwritten. And please, treat this exam, you're on your honor, but treat it as a proctored exam. Bring only this sheet with, your crib notes, whatever you want, a personalized cheat sheet on the back, whatever you want to write, and use only that for the final exam. There'll be some guidelines sent to you regarding the final exam. Roughly just try to set aside 3 hours. It shouldn't really take you that long, but that would be the maximum time you would need. And I'd like you to finish it in one sitting. And there's going to be a bunch of guidelines, plus there will also be an academic integrity form that I want you to sign and return to me. So I trust that you will uphold all your academic integrity and treat this accordingly. So with regards to the review, what I did was I just give you some hints as to the types of the problems, and I'll mention some of the formulas that you probably want to include on the exam. And you could pause this video to write down the solutions. I'd suggest you try these problems on your own, and then come back to this if you haven't already done so, and then come back to this video and check the solutions or check your answers, and then come back to this video and check the solutions. But there will be one question. Oh, there's the topic list also that I gave you on the and that's posted in Blackboard, telling you how many questions of each type to expect, and the point distribution as well. But there will be one question. The first question on the exam is using the formal definition of the Laplace transform. So I need to see the substitution into the formula. So with regards to what you might want to include on your formula sheet, is this formal definition that the Laplace of a function in terms of its formal definition as a definite integral is the integral from 0 to infinity of e to the negative st, and then times that function with respect to t. So you probably want to include that on your cheat sheet. So I'll write down a bunch of the formulas I'm going to suggest you include on your cheat sheet on this separate paper as we just quickly talk through this review. Okay, so there's the formal solution. One thing to note here, you do have to make this statement because in order for this first term to go to 0, this has to be, as b tends toward infinity, s plus 5 has to be a positive number. So you do have to make the statement at the end that s plus 5 has to be greater than 0. So therefore s is greater than negative 5 in this case. So make sure you include that. when you solve the problem. Then there's going to be 2 questions on Laplace transforms. You're going to be doing, I gave you 4 examples. I went over 4 of the 8 questions that are included on the review sheet here. And you're going to be doing some of the common ones like number 2 letter A and number 2 letter F throughout the exam. Definitely what I'm going to ask you is something like letter B and letter G. So letter B has to do with having to use, because of the rational exponent on this power of t with the denominator of 2 in the fractional or rational exponent, it has to do with the gamma function. So I did that work aside here, and so definitely expect something that's going to involve the gamma function. And then also expect something like letter G. So again, just pause the video and check out the solutions. I'm going to go through this rather quickly, but this will give you a way to see the solutions to these selected problems. And letter G is definitely a question I'm going to give you. Remember, with Laplace transforms, we can't transform powers, products, or quotients. Let me not say quotients because that all depends. But the powers or products we can't transform. So here we needed a special identity, and here are the 2 double angle power reducing formulas. So we had to transform sine squared by this identity, note the angle doubled, and then we took the Laplace of each of those terms. So expect something like this, and if I give you sine squared here, imagine what I'm going to give you on the exam. It's not going to be sine squared. There's a good chance, a hint, that it might be cosine squared. So include that on your formula sheet. And then to go to the next page, there's going to be 2 questions on inverse Laplace transforms as well. And here you can see there's 4. Again, some of the simpler ones, you'll be doing a lot of it, like letter A and letter D. You'll be doing a lot of that within the context of solving other problems. I like letter B and letter G again, where, again, you have a situation, so this is the inverse Laplace, but again, a situation where the concept of the gamma function is required. So be prepared for that. And then also be prepared for this concept of having to split up the integral into 2. And then notice the little modification here, because our table is k over s squared plus k squared. So we had to modify by multiplying inside by 3 and outside by 1/3. So that concept comes into play in other situations as well, but guaranteed something like letter B and G. And again, stop the video as needed to be able to review these solutions. Okay, well, there's going to be 2 questions on solving initial value problems using Laplace transforms. So definitely write down your transformation formulas here. So this is actually for number 4 and number 5, I'll say, where we're going to need the Laplace of the function x of t. Okay, that's just uppercase x of s. Then the Laplace of the derivative of x of t, and that is s uppercase x of s minus lowercase x of 0, and Laplace, this one's going to be needed not for this number 4 here, but for letter A, but for the next question. Laplace of the second derivative is s squared uppercase x of s minus s lowercase x of 0, and then minus lowercase x prime of 0, your initial conditions. So definitely you want to make sure you know those transformations. And you can see number 4, kind of a straightforward problem where You take the Laplace, remember the one thing when change them to functional notation, use functions of t. Take the Laplace, and I guess I made some mistakes here. Sorry about that. At this point, that should be up all the uppercase x of t's here. Sorry about this. Should be x of s's. So that's an x of s. All these are x of s's. And I missed one more up here, and a couple more up here. Hope I didn't do that in the next question. So the transformation gives us a function of s. Okay. Alright, so that's all fixed, and you can see I tried to distinguish between the uppercase and lowercase x's by using a little bit of curvature for the lowercase x, where the uppercase x is more of a stiffer. And here I'm fixing these ones too. Right, so I apologize for that. Okay, but that solution to that one's kind of straightforward. Okay, so then the second question is going to be like letter D, where you've got a second derivative. So I reminded in the solutions here the transform for the second derivative. But after applying the second derivative, you can see at this point, when we solve for x of s, again it's x of s, hopefully I've got them all corrected here, yep, looks like it, we have the need for partial fractions. So you will encounter some situation where partial fractions will be necessary. Okay, so I'll just leave that part of the solution for a second there, and we'll slide it down just in case your pause it is necessary. So sliding it down and showing the rest of the solution. So that's the second half of the solution. So make sure you're ready for the concept of partial fractions. Okay, and then there is a question on system of equations. And regarding the systems of equations, something similar to number 5, letter A. I mean, all of them are good to practice, but these are a little bit more indicative of the types you're going to see, the ones I'm showing you here. So these are basically, if we were to have a formal lecture, I would spend a few days reviewing as I normally do, and we wouldn't go over every problem. I would be going over typically the ones I'm showing you now. So here's the solution to the systems of equations. You can see that you have to use Cramer's rule, so you set it up so that all the x of s's, and once you take the Laplace, you substitute the initial conditions and then set it up so you could use Cramer's rule. I showed it here where I took the denominator, calculated that. Typically it's, this one wasn't factorable. It came out as s squared plus 9. Sometimes it's factorable, but whatever the case, you just deal with it. But then I calculated the numerator of the solution for x, and you could see at that point took the inverse Laplace. This was a case where I had to split it up and modify. I solved for x of t right away, and then I went on and did the same thing for y of t, as you could see. Okay, so be prepared to handle a system of equations and using Cramer's rule. So again, quickly, here's the top half of the solution. So again, pause it as needed, the video that is, and then here's the bottom half of the solution. Okay, and then we get into our work with series. And with series, I wrote down the assumptions that we make in the series solutions and their derivatives. But for questions 6, 7, and 8, at the very least. Now, on your cheat sheet, you could write anything you want, but obviously these few things I'm showing you here are things that are kind of imperative. So we always assume with our series solutions that y is the sum as n goes from 0 to infinity of c sub n x to the n is a solution. And then we substitute y and its derivatives. So if you recall, we had its derivatives, y prime is the sum as n goes from 1 to infinity of n c sub n x to the n minus 1th. And we had the second derivative as well, which was the sum as n goes from 2 to infinity of n minus 1 c sub n x to the n minus 2. So those formulas. Now write down anything you want on the back of that cheat sheet. I mean, these probably the main things that I would say you have to know. You've got the table and basic series on the front side. But then write down anything you want on the back, examples, whatever. It's all fair game as long as it's handwritten. And again, please keep your academic integrity and try to restrict yourself only to that sheet. And there will be an academic integrity form that I'm going to ask you to sign as well. Okay, so you can see the solution here. Just a couple quick comments. When you make your substitutions, and you always, or if there's a variable in front of the sum, you want to distribute that. And remember, we're allowed to do that because this is just an infinite polynomial. So certainly you can multiply x inside of a polynomial. But at that point, you want to look at the powers on x and look at the indices. And if they differ by the same amount, then you're able to get away with just a shift to use the identity principle. But if the differences differ, then you're going to have to count off a term, one or two terms, as many terms as the differences differ. And in this case, it's one term. So you count off the one term here, and just note that immediately after you count off that term, you have to determine what it is, and that's by a comparison. And comparing the reals here, the one thing to note is that if you plug a 2 in here for n, you get a power of x. You get x to the first. And similarly here, you get x cubed. So the only real number is c sub 1, and on the right there's no constant, so therefore c sub 1 is 0. So immediately solve for that c sub 1 if you have to count off a term like we did in this example. And then once the differences differ by the same amounts, then you can shift the larger down. It's always easiest to shift the larger one down. And then the powers on x will match, and the indices will match, and then you could use the identity principle to find the recurrence relation. And if they differ by 2, the values of c sub n and in your recurrence relation, then you're going to have to look at the evens and the odds. Okay? And I was very explicit here in the solution as I was when I presented this to you in the lecture. So just take a minute and I'll show you the solution again. Here's the top half. Okay. So if you have to pause the video, do so. And here's the bottom half. And this question asks you to give it into as an elementary function. Okay. They always, in the review here, it says to find the radius of convergence. I didn't even bother doing that in these solutions. I'm not going to ask you to do that. So don't worry about the radius of convergence, but do worry about expressing it as an elementary function. Okay. And there were little tricks involved, so look back at the old videos if you need to. But I tried to be explicit in these solutions for you. Okay, so we're almost done. 2 more questions. And the next one is a second order. Differential equation, series solutions. So pretty much the same concept. Substitute in the derivatives and the function itself as a power series. And notice that in this one, they differed immediately by the same amount. So just a shift accomplished the task of setting it up so we could use the identity principle. And then again, we got the recurrence in terms of evens and odds, so in terms of C sub zeros and C sub ones. And one thing to notice about this, when the way I've structured the solution for you, usually in class I'm not this explicit because I would ask you guys to think a little bit. But here, the way I've written it out, notice that if the solution is in terms of C sub 0 and C sub 1, I first wrote out the general solution for y, our assumed solution, but then I broke it up to be in terms of the evens and the odds, and then made our substitutions in terms of C sub 0 for the evens and C sub 1 for the odds. So hopefully you'll find that a helpful concept. This one required a little bit of trickery toward the end, where we had to multiply inside by 3 and outside by the 1/3 to make the powers on 3 match the powers on x, so that we could put it into a standard summation form that is ultimately given in terms of our basic series that are listed on that table. So again, I think you had enough time to see it all, but just to give you one more minute, if you like, there's the top half of the solution showing how we generated the recurrence relation. We got the values of the constants, and then here's the bottom half of the solution, which shows you the rest of the substitutions and the transformation into the basic functions, elementary functions. Okay, so then one more question, and this is where we call this non-elementary solutions, or solutions near ordinary points, series solutions near ordinary points. You start off exactly the same way, where again you make the assumption that C sub nx to the n is a solution. There's the derivatives, make your substitutions, make sure you distribute the variables here. Here I separated into 2, distributed the x squared, note the power on x changed to n because you're adding 2. But then we had a separate sum, which was 2 times that integral. And here's the little trick of being able to start at 0 for these first and third series. Like, notice how between the second and the fourth, the indices differ by 2, or excuse me, the powers on x differ by 2, n minus 2 and n, and the indices differ by 2, n equals 2 and n equals 0. So by shifting down, this one will match this one with regards to setting it up so we can use the identity principle. But the first and third terms are the issues, because the powers on x are good, they're all x to the n, but the indices are not good. But it really doesn't matter because, and look back at the video, the initial video for more of an explanation if you like, but we're able to start this series at 0 because consider that when n is 0, this term is going to be 0 because there's an n in there, and if n is 0, that's 0. And similarly, when n is 1, the n minus 1 is 0, which wipes out that term. So the only terms that have an effect are when n equals 2. So you're allowed to start when n equals 0 because those first 2 terms are 0. And similarly here, you can start at n equaling 0 because when n is 1, that's a significant term. But if n was 0, that n causes this to be 0. So it's a special situation, and again explained in the lecture, initial lecture as well. So then we apply the identity principle. A lot of times what happens is these things factor and you get cancellations. they shouldn't really turn out to be too ugly. And then again, they differed by 2, c sub n plus 2 and c sub n, that is. So you had to do the even odd thing again. And as you can see, I split it up once I found the coefficients, tried to make it a little bit easier. And this one just says to state the to find a power series solution. It doesn't say to determine the elementary function. Okay, so but you do have to give the sums. All right, and you can see the summation, alternation of sign, powers on the base of 2, and powers on x were even for the c sub 0, and odd powers for the c sub 1. So respectively a 2n and a 2n plus 1 for those powers on x. Alright, so just to show the solution again, in case you want to pause the video. I don't think I went too fast, but there's the first half up to the recurrence relation, and then so pause the video and check it out, and then there's the second half of the solution. Alright, so it's been fun, I guess. I mean, a lot of work. I know that doing these videos were very time consuming. Hopefully you enjoyed them. I really missed being in class because there were a lot of jokes. It really could have made you laugh, I'm sure, more than I did, but it was just under time constraints and unfortunately couldn't squeeze in the standard jokes. But I think you guys, have known me long enough, so hopefully you'll still consider me as a good instructor. And I just wanted to wish you all the best, not only on the final exam here, but in all that you do in the future, academically and in life. And I know there's going to be a lot of good success stories, so keep in touch with us, because that's part of what's so rewarding about my job is to hear you guys succeed and do well in your future endeavors. So keep in touch, and again, I wish you the best of luck, not only on the exam, but in all your future and academic endeavors. Oh, and if there's any solutions to other problems you want to see, or just feel free to email me, call me anytime, and I'd be more than happy to help you out. So take care.